Yeah, I was looking up when was incompressibility first discussed, and I came across an article. It was an article in Humanities, but it was really interesting. I was looking back at some experiment that somebody called Schwammerdam, a Dutch person, had done in the 18th century, 1757. They had done the following experiments, which are amazing. They weren't looking at incompressibility. They were looking at what's called animal spirits. Right? They wanted to show, to prove that there was an animal spirit, or maybe that there wasn't. I can't remember. In any case, they did those experiments. So they had this syringe, and was hermetically sealed here. And there at the top, there's a thin tube, and at D here, there's just a little drop of water that's suspended by capillarity at that level. And then inside the syringe, they put the heart of a frog, and it was beating. So I don't know how they kept it beating. Maybe you could keep a heart beating for a while, or maybe you put. It's not explained. I must look it up. But so it was contracting, and as it was contracting and relaxing, that drop will go up and down, right? It will say a very remarkable descent in a very remarkable, surprising manner. Oh, actually, no, it contracted once and it dropped, just showing that there was a change in the volume in that cavity here. And then later they did it with a thigh muscle from the frog, such a way that a nerve was coming out, and here it was sealed, at B it was sealed also tightly. And again, there was a drop of water here, there's no letter. And then if you pinch the nerve at C, the muscle will contract a lot. And there they saw no change in the level. And so they concluded that this experiment was no good. But we, with hindsight, we could see that this was the first time that it was proven that a change, a large deformation of muscle, large deformation of a soft tissue did not yield a change in the volume. And at the heart, for the heart, there was a drop. Oh yeah, sorry, it went from C to D. That's what it is. Now I can see it better. There was a drop once it contracted, but that's just a reflection of the fact that the heart has cavities inside, right? The ventricles. And so when it contracts, it's just the air inside that's contracted. So overall, the volume has changed, the volume of the heart, but not the volume of the muscles that make up the heart. It's just because there's this cavity inside. Whereas in the muscle here, there's no cavity. And so even though it deforms a lot, there's no change in volume. Amazing experiment. Really pretty hard to do even today. Maybe I should have a final year project on that. And later on, in fact, I went here. You could see here that it says the Bibliothèque Interuniversitaire de Médecine. At the time, I was in Paris, so I went to that library, medicine library, and I asked for that journal, that book, in fact, from Schwammerdam, and they took them a while, but they brought it to me. It was all dusty. It was amazing, and I looked. It was huge. It was a really big book, and I had to go like this. It was like really Harry Potter. And eventually, I came to that picture. And this picture here is really interesting because what it is I introduced like a copper wire, and he was trying to stimulate the muscle electrically in the 18th century already. But I think it wasn't clear if he managed. Yeah, I think that was a silver wire, and he put it in touch with copper to create a current and make it contract. Again, with the little drop here. Amazing. All of this, hundreds of years ago. All right. So today we are going to do some more experiments, so I'm going to present them anyway. and try to model them using mathematics. Right, so for that experiment, we are able to model incompressibility using the condition that the determinant of f must be 1, always and everywhere. And we saw in the last lecture, we saw that what that meant for the stress-strain relation. Right, we saw that it led to sigma equals minus pi, where p is arbitrary and we have to get rid of it somehow, or determine it one way or another. And it's due to the constraint of incompressibility. And then you have this fairly simple relationship where B is the left Cauchy-Green deformation tensor and so on. For B minus 1 is its inverse. So you see everything is nonlinear. B is already nonlinear in the stretches and the strain. W1 and W2, these are shorthand notations for dW, di1, dW, di2. I1 and I2 might also be nonlinear functions of the deformation. Everything is highly nonlinear here. And then I showed you a couple of examples of popular W's, those that are used in the literature to model observed behavior. So really here we are at the root of science, right? There's a phenomenon, you collect the data, there's a theory, you come up with a model, and then you try to make the two fit. If you manage, great, it's a good model, and it works as long, and you can use it for anything as long as there's still correspondence between data and model. And if it doesn't match, then you have to abandon the model. So the easiest way to test a model is to do control experiments in the lab. And the most popular one, if you go to the engineering building there in the workshops, you will see that there are what are called tensile machines. The most popular one is the simple tension test, because it's easy to implement. I remember showing you I remember showing you a YouTube video of it. Simple tension test. You need a machine that will take your sample. So you take either a band or a strip or a bar or a cylinder, and then the machine will grip the top and bottom and then just pull on it and measure the force as it's pulling and the stretch as it's deforming, and give you that data. All right, so it's just to represent it. If you had a bar which was like this in the reference configuration, it's going to be stretched. I'm a terrible drawer compared to Giuseppe, but I hope you get the gist. It's going to be stretched into this deformation, this shape by the application of a force, right? So here we have the reference configuration, and here we have the current configuration. What I do is that I apply force. I measure the area. That one, that's going to be little a, and that one is hard to access, as you can imagine, because it keeps changing. The one that's easy to measure is capital A. I just measured at the beginning using a caliper. then the machine tells me F, and the machine tells me the stretch. Right, so I'm going to put some, let me see, 1, 2, 3, no. I'm going to put some, one is like this, yeah. Some axes. Let's say that's the one axis. 3 axes. And I could see that if everything goes well, if it's a homogeneous deformation, if the rectangle, the cuboid is turning to another cuboid, longer, thinner, but everything stays neat, and there's no homogeneous deformation, there's no bulging, there's no slanting. I will see that it's going to be described by a deformation like this. Each element is going to be stretched along those 3 directions, x1, x2, x3, with the stretch lambda 1, lambda 2, lambda 3. So the deformation gradient is going to be a diagonal matrix in that coordinate system. F F for me like this. What else can I say? I'm only applying a force along the x1 axis. So I'm pulling like this. So, oh yeah, I should have shown you. I have one here. Let's see. That's when I was doing experiment on silicon. I will just cut out little samples like this, right? So the grip will be on top and the bottom like my finger, and then the machine will just pull and measure the force it takes to pull it like this. So by symmetry, and isotropy, we can conclude that lambda y is lambda 3, right? Whatever happens in the 2 direction also happens in the 3 direction. I'm just pulling like this, so it's going to contract the same in this direction as in that direction. If it was anisotropic, if there was fibers in the cross plane, then maybe it will contract more in one direction than in the other. But if it's isotropic, everything should happen the same in the horizontal plane. By symmetry, I have this, and then by incompressibility, I must have that of F, which is the product of the 3 stretches here, equal to 1. And so that leads me to lambda 1, lambda 2 square equals 1, and so lambda 2 minus a half. So simple tension is going to lead to, if I call lambda the stretch, that's measured along the uniaxial tension direction, I'm going to have this lambda 2 is minus a half, lambda 3, lambda minus a half. That's simple tension. And now I can just plug this into my stress-strain relationship. B is going to be FFT. Since F is diagonal, it's just going to be F squared. B minus 1 is going to be the inverse. And so I can just write here directly that sigma must be minus P times the identity plus 2W1B. It's going to be lambda 1 squared, lambda 2 squared, lambda 3 squared. So to compute lambda 2 and lambda 3 squared, I just use the iteration above. And then I have minus 2W2B minus 1. So I take the inverse of that diagonal tensor here. And that's easy. It's just the inverse of each diagonal term. Okay, so the stress only has 3 components. The first one is sigma 1, 1. They are just the diagonal components. And then the second one is sigma 2, 2. And then the third one is the same as the second one. So that's the maths. That's my model. Or actually, no, that's the result of all this, all these chapters we've gone through, describing the formation, describing the stress, describing the work and the stored energy. Comes down to this. And now if I apply all this to my problem here, I know that the stress is the force divided by the cross-section area. So I guess I should write it here. Do A, that's going to be L2, L3. If this L2, L3 are the, the length of the edges in the 2 and 3 directions. And little a is going to be L2, L3. But they've both been stretched by lambda 2 and lambda 3. So that's going to be lambda 2 squared because lambda, well, it's going to be lambda minus 1 capital A. I hope you can read this. For here, I'm just showing you how I can measure sigma 1, 1. The machine is going to give me F and lambda. With my caliper, I've measured capital A. And so I can just put that in a spreadsheet and compute sigma 1, 1 for each F and each lambda. So that's the stress in the one direction. In the 2 directions, they are free of any constraint. And so I'm just going to write that they are both 0. Okay, so well, the last line, that's just the same as the previous one. So I only have 2 equations, sigma 1, 1 equals this, sigma, and I want to get rid of the P. So I can find P from the second line. Tell me that P is going to be, oh, here I made a typo. So here I wrote W2, but it should have been W1. So P is going to be 2 W1 lambda minus 1 W2 lambda. And now that I have P, I can put it back to the first line. And I've managed to eliminate that pesky Lagrange multiplier arbitrary scalar. I actually found it, and now I can get rid of it. So if I substitute this into the first line, and I collect the W1 terms, and then collect the W2 terms, and tell me if I made a mistake, but I think this is what I get. And in fact, I can rewrite it. It's not obvious, but Rivlin noticed that. You can factorize. Yeah, if you look at these two terms here, you can see that the difference between them is lambda cubed, right? If I multiply the last one by lambda cubed, I get there's 3 degrees difference between those two terms. And it's the same for those two terms. There's also 3 degrees of difference. So there should be a way to exploit this if I pre-multiply by lambda minus 1, I should get this. Am I right? Am I right or am I right? Lambda, I'm just checking now if I do lambda minus 1 times lambda squared, I'm going to get lambda, yes. And if I do lambda minus 1 times lambda minus 1, I get lambda minus 2. So that is correct. And now I can see that the two bracket terms are in common and factorize. Sigma 1 equals 2 lambda 1 times W1. Very neat expression. So this is it now. These are things I can measure. Sigma 1 I showed you earlier, that's F times lambda divided by A. And lambda, I measure that with the machine. And then when I do that, I get a set of data. And I'll show you now an iconic set of data. It's from somebody called Traylor. Actually, how should I show it to you? Yes, here. So I collected it and I plotted it. And I'll give you that data if you want. But these are experiments made on rubber, right? On something like this, natural rubber. Well, not this one, right? Every piece of rubber might be a bit different, manufactured differently from a different company. But in 1947, Traylor in the UK, he did those experiments. He didn't have one of those modern machines that just gives you a spreadsheet with all the data and maybe will do 1,000 measurements in the time it takes to stretch the material to break point, or even more. 2,000-3,000 is just incredible. It's almost continuous measurement. Indeed, instead he just had a strip and he just adds weights. I think he had 14 weights, and for each weight, from the weight he knew the stress, right? That was giving you the force, and then for each weight, each deformation, he measured the new length, and he got the stretch that way. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14, 16, 18, 20, 22, 24 measurements. and it has this nice curve here. So you can see in the beginning, the slope is quite low. In the beginning, it's easy to stretch. Then it increases with the force increases with the stretch, and then it increases very rapidly near 7, right? Here you can merge, you reach sort of limit, and it becomes really hard to stretch it further. And if I apply more force, it will break, clearly. But look, that's 7, right? So it means it's 7 times its original length. So it's 600% extension, enormous. Some elastomers, some rubbers can stretch even more than that, 1,800 times percent extension before breaking. So that's the curve, and you look at this and you say, okay, well, which material is it? Is this one of those that I was telling you earlier? In fact, Taylor, he was a physicist, and he developed a statistical. So maybe I should just sketch it. He's developed a statistical mechanics model for elastomers. Taylor 1947 rubber data. But clearly, you could do this at home using a similar apparatus to his. So he developed a statistical physics model for the chains inside a rubber, and he said, this is what I got in the end. I got that W was to be like this, what is now called the neo-Hookean model. And then they say, well, if that's my W, that's what I will expect. If I put this into my formula above, remember W2, that's dWdI2, since there's no I2 dependence here, that's going to be 0. So neo-Hookean model predicts that sigma 1,1 should be W1. That's just going to be mu0 over 2 times 2, so it's just going to be mu0 times lambda squared minus lambda minus 1. Now, if you plot this function, you will not get that blue curve I have there. The best you can hope is to have a good fit at the beginning, and then it's going to go like this. Neo-Hookean. It will never, okay, maybe I gave the wrong impression here. It will grow, but very slowly. It will go like this. It will never capture that stiffening at the end. And so in that respect, it's disappointing. Let me show you, in fact, how it looks like. Here I have it. Yeah, so because all you can do now is play on mu0, right? If I look at the formula, that's the relationship between sigma and lambda, and then I can adjust mu0 to get the best fit possible. So if you do that for the beginning, you will get this curve, these black dots here. I said, okay, It's not going to work. I'm not going to be able to capture all the data. I say, let's just try the 1, 2, 3, 4, 5, 6, 7, 8 first terms. And it doesn't look too bad, right? It seems to be following the trend. And then if I was to do the fitting with all the rest, I would have to adjust my mu0. And the best I could get is something like this red curve here, which is clearly terrible, right? It's kind of hooky at the beginning and then really far. And if you look at the errors, oh, sorry, that's not it. At the errors generated, they are dismal, right? If I do the global fit, I get this, the error is so big that I could fit it in the plot here. But you can see it starts at 40%, and then it's at least 60% error, probably goes above 100%. Then it's a bit better at the end, but it's still really high, right, in the 20%. Terrible. Wait, again, I think I'm wrong. I didn't choose you the right one. Yeah, sorry, this is it. So terrible for the best fit on all points in the region, up to 50%. And for do just the first 5 points is not great either, right? It goes down here at about a couple of percent, but still around 20%. So the neo-Hookean model is just no good for rubber. No matter how you want to adjust that mu0, it's not going to work. Okay, maybe I should stop the recording, break it up.